Hello everyone, welcome to Midas webinar on PSC Composite Girder Bridge. My name is Saurabh Tak and I am Technical Support Engineer at Midas, India. In today's webinar, we will discuss everything from modeling to the design of a PSC Composite Girder Bridge using Midas Civil. Let's start with the webinar. This will be the flow of my webinar. I will introduce you to the structure first, then we will move on to the modeling and analysis part, and after that we will briefly cover the design of PSC composite bridge. Let's discuss the bridge dimension first. We will be modeling a PSC composite bridge of span 40 meters, total girder depth of 2.2 meters, deck width of 6.4 meters and deck slab depth of 0.2 meters. Let's look at the cross section of the bridge. The center to center distance between the girders is 1.6 meters and the cantilever part is 0.8 meter as shown. Now let's look at the girder section of the bridge. The girder section is a SY6 precast beam of depth 2 meter. The girder dimensions are as per the standard sections available in bridge beam manuals. The girder sections can directly be selected from a predefined database of standard sections available in Midas Civil as shown in the image on the right hand side. Let me discuss the tendon profile for this section. The tendon profile is provided for the standard SY6 beam as per the bridge beam manual. The image on right side shows the pre-tensioned strands provided for standard SY6 beam section using tendon template tool of Midas Civil. Let's move to the demonstration part of the webinar. In the demo, everything from modeling to the final design will be covered. Let's start with the modeling of the bridge. Let's open a new file. Okay. Here I will show you how to define material properties and sections in Midas Civil. Also we'll discuss the time dependent properties in this part of the webinar. So let's define the material first. We'll define the material for the girder. So I have selected the Eurocode 4 and C50-60 grade concrete. I'll press OK. The material is added. Similarly, material for the deck slab can be selected and the tendon, steel material for the tendon can also be provided. In section tab, we have several options to provide PSC section, composite section, steel section, tapered sections. For our demonstration purpose, I'll show you how to define a PSC value type section from standard database. We have a standard database of PSC value type section. First I'll name this section as section 1. From the database I'll select the required section. So we have an option based on the codes as per these countries. We'll select UK code. We'll select UK SY section as discussed in the presentation. So SY6 beam is selected now. The properties for this beam is generated over here. Let me provide some design parameters. Here T1 is the depth of top flange, where I will put a small value because we don't have a top flange in our girder. T2 is the depth of bottom flange. I will provide it as per the girder properties. BT is the thickness of web. I'll provide it as per girder properties. ST is the depth of the girder, which is 2 meters. The thickness for torsion is for the torsion check calculation. I'll provide it as 0.2. For shear check, position needs to be given. I'll give 0.5 for Z1 and 1.5 for Z3. We'll press OK so that these properties are calculated by the software itself. Once I press OK, the girder section is generated now. Let's see how to define a composite section and using the girder section we have just defined. I'll go to composite tab. I'll name the section as composite section. I'll select composite PSC section. based on the drawing, we'll give the width of our deck as 1.6 meter, depth of our deck as 0.2 meters, and I'll import the girder section. SY6 is available over here. I'll just click OK, and the section is imported. We'll give properties for the girders and the slabs over here. So for the slab material, I'll give 40-50. For the girder material, I'll give 50, C50, C60. Once I press OK, these properties are generated. We'll change the offset of this section to center top, and we'll press OK. The offset is changed now, and you can see the properties of the section before composite and after composite in this tab. Once I press OK, my composite section is generated. Now let's take a look at time dependent material properties. Let's take a look at time dependent material properties. Time dependent material properties are required to take the effect of creep and shrinkage in the analysis. We'll go to time dependent material tab. We'll click creep and shrinkage. Press add button. Let's define time dependent properties for girder section. So I'll give it a name C50 60 grade concrete and select the code as Euro code. FCK value is 50,000, and will provide a certain notional size. It shall not be 0, and this notional size will later be updated in construction stage and composite section for construction stage. So these are the other parameters, that is the type of cement and the age of concrete at the beginning of shrinkage, so which is usually given as 3 days. Once we click show result, we can see the variation of creep coefficient with time and the variation of shrinkage coefficient with time. So this can be done with just a click of a button, and this property, time dependent properties, are generated for the girder section. Similarly, we can do this for slab section as well. Now let's define the compressive strength variation with time for the girder section. I'll define C50 60 grade concrete. We'll select the European code. We'll give the mean compressive strength for the concrete. I'll provide it as per the code 1000. Once we click redraw graph, this is the variation of compressive strength with time. Once I press OK, the variation of compressive strength with time is generated. Now we need to link these properties with the defined property. So I'll click material link. I'll select C50 60 grade concrete for shrinkage and for compressive strength variation. I'll select the material type, and once I press add, these properties are linked to this particular material. Same process is to be repeated for the deck slab as well to generate the creep shrinkage properties for deck slab. Now let's move to our base file for the subsequent modeling of the structure. So this is the base file of the model. As we have already seen how to create material and section in Midas, I have already defined concrete material for my girder, concrete for my deck slab, steel for my pre-stressing strands. I have defined the composite section and section for the diaphragm as well. Moreover, we have created the time dependent material properties, that is the variation of creep and shrinkage with time. Also, we have defined the variation of compressive strength with time, so that software can calculate time dependent material property for the structure. Moreover, we have defined the reinforcement for the composite section. In the section manager tab of Midas, we have defined longitudinal reinforcement as well as shear reinforcement, so that can be taken into account during the analysis. Let's go to the pre-stress composite bridge wizard. In a structure tab, we have pre-stress composite bridge wizard. In Bridge Wizard, we have 5 tabs. The first tab is Layout tab, where we define the geometry of the structure. In second tabs, Section for various component and material for various bridge component is defined. In Tendon tab, we define the tendon profile for the already defined sections. In the Load tab, we can select the position and the value of loads. Here the live loads are also defined. In construction stage, we can define the duration for different construction stages. Now let's look at the Layout tab. Also, I can open up already saved wizard using open button. We'll be using this wizard for the subsequent modeling. Now we'll be defining 40-meter single span PSC composite girder bridge. So I'll define a precast girder type bridge. I want all my elements to be frame type. We can select plate element here. I'm defining 40-meter span with a deck width of 6.4 meter. For simplicity, I'm not giving the offset and the skew angle at the supports. We can provide curvature to the bridge as well using radius option. We can also provide the structure with a substructure using the substructure option. Currently I'm not using for simplicity. Now let's look at the section tab. In section tab, we define the deck thickness first. We define the deck material, girder material to be used, diaphragm material to be used. We define the number of girders and the offset of those girder based on this guide diagram. Now for the diaphragm, we select the section we have already defined for the diaphragm. So we can define the different diaphragm section at the PL location, at the end support and the intermediate diaphragm. We can define the number of divisions so that a number of diaphragms can be decided. So currently I have put 3 divisions, that is 2 intermediate diaphragms to be provided. For the deck elements, I have defined 1.5 meter spacing center to center. Similarly, for the girder information, I have selected the composite girder section. Now we have seen the section tab. Let's move on to the tendon tab. In tendon tab, we can define the tendon profile as per the guide diagram shown here. Also, from here we can select half kind of tendon, curved type of tendon as well. Moreover, we have a standard database of tendon for PSC value type section. Here we can select the section from there. Before doing that, we need to define the tendon properties that can be defined from the wizard itself. So I'll define this tendon properties or strand property. So I'll be using internal pre-tensioning strands of material 15.2 mm dia strands. The total area will be selected based on the strand dia. I'll press OK. So our property is selected. Now based on the code, we can select our section UK, that is UKSY 6 section, and on pressing OK, this will generate the tendon profile for this particular section. So I have already generated the tendon profile for SY6 beam. So that's how easily we can generate. Moreover, we can edit the tendon profile, tendon spacing, number of tendons as per the guide diagram shown here. As we have seen how to define tendons in PSC Composite Bridge Wizard, now let's look at the Load tab. In Load tab, we define the position of crash barrier and median. For that position, loads are defined. So when we check on before composite load, it applies the wet concrete load onto the girders. Also we can check on the self-weight and wet concrete load is calculated as per the density provided, that is 25 kilonewton per meter cube for a thickness of 0.2 mm. We can check on formwork load as well. So I will consider 0.3 kilonewton per meter square formwork load. I'll consider a barrier load of 5 kilonewton per meter. I'll consider wearing surface load for density of 22 kilonewton per meter cube for a depth of 65 mm wearing coat. I'll define the live load over here. I'll select the Euro code. I'll define the traffic lane. So I'll define lanes at a distance of 2 to 5 meter from the left end of the girder. I'll define the vehicle. For simplicity, I'll consider LM1 type vehicle. Close it. Now we have seen the load tab. Let's move on to the construction stage tab. In construction stage tab, we have this guide diagram. Based on that, we have already predefined construction stages. We just need to define the duration of days for each construction stage. Also, we have an option to define reinforcement over here. We have already defined the reinforcement for this. So longitudinal and shear reinforcement has already been defined in the base file itself. So let's press OK. My structure is generated now with all the construction stages. Now let's look at the work tree got generated using wizard. The nodes and elements are generated. The materials, we have already created the 3 materials. The dummy material is generated for the dummy elements. The dummy sections are section number 4 and section number 5. The section number 4 is the edge element for the deck, and section number 5 is the cross beam element. For the reinforcement, we have already defined in base file. The wizard has also generated the composite section for construction stage, was already defined in the wizard. Based on that, composite section for construction stage is defined. Here we can see the required material is selected for the deck slab, but the age of the element and the age of the material is coming to be 0, which will update once we look at the other options. For the supports, these at the support locations, the fixed supports are generated. The fixed supports are connected to the bottom node of the girder using elastic links, and using rigid links, the top nodes of the girder are connected with the bottom node of the girder, as you can see. In the loads, we have self-weight that got generated. Then we have wet concrete load, which is applied as UDL onto the girder elements. Then we have formwork load, which is again applied as UDL on the girders. Then we have nodal load, that is the crash barrier load, which is applied as nodal load at the crash barrier location. The wearing coat load is applied as UDL on the cross beams. The tendon pre-stress is also applied, as we can see in the table. The tendon pre-stress can also be checked in the pre-stress, in the load pre-stress and tendon pre-stress. As you can see here, the tendon stress for the tendons are applied for the various tendons. Now let's look at the tendon profile. So these profile are generated using the wizard. For moving load, as we can see, the moving lanes are defined. The moving vehicle is also defined, but the moving load case is not defined, which needs to be defined in order to link the lane to the vehicle. We'll define it in a while. Let's look at the construction stages first. In the construction stage, as we can see in the first construction stage, the substructure, girder and diaphragms are activated. at the age of 0, which will update one. Okay, in stage 1 boundary group, the substructure supports are activated, rigid elastic links are activated. In stage 2 dash 1, the wet concrete load and the formwork load is getting activated. In stage 2 dash 2, the dummy beams are being activated, that is cross beams and the edge beams are being activated, and the load of wet concrete and the formwork concrete is being deactivated in the same stage. In stage number 3, the crash barrier load and wearing coat load is being activated. Stage 4 is to consider the long-term effects of creep and shrinkage. So a duration of 10,000 days is given. Now let's look at the moving load cases as we already discussed. So I'll add the moving load cases. I'll see one case. I'll check on the ignore xi factor. LM1 case for both the lanes. Okay. I'll create another case. LC2 no xi. I'll ignore xi factor. I'll not check on ignore xi factor. I'll click OK and close. Now let's update the age of concrete in construction stage. So the substructure girders are activated at 0 age, which is not correct. There should be initial age to those. So I'll just modify those ages. Click apply. For the cross beam ages, certain age should be provided for the initial property calculation. So I'm providing 14 days age. I'll click OK, apply. Similarly, in the composite section for construction stage, the age needs to be updated. So I'll put 14 days in this as well. Okay. So now age of concrete is updated. Now let's take a look at the analysis options. In construction stage analysis, this is the construction stage analysis control data generated from the wizard. Now let's look at time dependent effect control. Here creep and shrinkage is selected by default. To calculate the effect of creep, time steps are generated automatically by the software based on the duration provided for the construction stage analysis. These are the options that are checked on by default to accurately calculate the tendon losses due to long-term effect. Once we press OK, the changes are saved. Let's look at the other crucial parameters. We need to check on initial tangent displacement to get the correct deformation of the deck slab after the analysis. Also, beam section property changes with tendon needs to be selected to take the transformed area for the analysis. If the constant option is selected, the transformed area is not considered for the analysis. Also, in frame output, we need to select self-constrained forces and stresses to consider the difference in time duration for the activation of girder and the deck slab, which creates eigenstresses between the girder and the deck slab. Once we press OK, the option and the changes are saved in the construction stage data tool. Now let's take a look at main control data. In main control data, consider reinforcement for section stiffness calculation shall be checked on to update the stiffness as per the reinforcement provided in the composite section. We press OK. These changes are saved for the analysis now. Also, I want to update the notional size of my section. I'll go to composite section for construction stage. I'll click update all edge. So it is updated automatically. I'll click OK. I'll close it. Now my structure is ready for the analysis. I'll run the analysis. So my analysis is completed without any warnings. I'll check my results now. So I'll check the bending moment diagram for the girders. So during construction stage 1, this is the bending moment diagram for the structure. The construction stage 4, this is the bending moment diagram. For the post composite stage, we can get the envelope, moving load envelope for different cases as well. Now let's look at the deformed shape of the girders. So this is the deformed shape for maximum case. So this is the for the moving load envelope case. Now let's check the deformed shape during construction stages. So this is the deformed shape for construction stage. So we have to check the stage real displacement to get the displacement for construction stages. This is the deformation for construction stage 1. Now let's look at the some crucial results that are very important for composite section analysis. So we have self-constrained forces during construction stage. So we are using composite materials, that is the girder is activated at different stage and slab is activated at different stage. So there will be self-constrained forces due to the interaction. So this is a table of the self-constrained forces due to interaction between the girder and the composite slab. Similarly, let's take a look at the part-wise stresses in composite section for construction stage, beam force and stresses. For all the cases and all the construction stages, we can get the part-wise stresses. As we have the permissible stresses for different parts, it's easier to use the part-wise stresses for our design purposes. So this is the table for part-wise stresses in beam. So part 1 is the girder and part 2 is the section. These are the forces and these are the stresses in those parts. Also we can also take a look at the tendon loss. So in tabular form we can get the tendon loss for different stages. As you can see, for stage 1 we are getting the loss after immediate loss after stress after elastic shortening loss, stress in tendon after creep shrinkage loss, stress in after relaxation loss. So everything is given with a final ratio of stress in the tendon. So we can change the stage from here. In the stage 4 I can check the final losses and the final stresses in tendon in this table. This can also be seen in graphical format using tendon loss graph function. So for different tendons we can select in which stage we want to check the losses. So this is the tendon loss graph for that particular. We can save it as image file and can be used for reports as well. As we have seen some important results for PSC composite girder bridge, now let's move on to the design part. Before moving to design, we will define some load combinations. I'll make sure that I am in post CS stage. I'll select the load combination tab and I'll go to concrete design. I'll use auto generation command to generate load combination. I'll select Euro code here. I'll check on both in this. I'll select the live load case. So we have defined two live load case, one for characteristic, one for frequent combination. I'll press OK. I'll press OK. Now as you can see, 4 load combinations are generated with and without live load. For strength case, for serviceability we have with live load, without live load cases as well. So we'll be using these load cases for our design. as we have already seen how to create load combination in Midas. Now let's take a look at PSC Design tab. In parameters, we'll select the parameters as per Eurocode 2. I'll check on all the output parameters by clicking select all options. I'll press OK. Then we'll go to PSC Design Material. Here we have defined C50-60 concrete. For that concrete, main bar material and sub bar material shall be defined. So I have defined all this material for rebar, for the slab concrete, for the rebar of slab concrete. Similarly, for the deck material, that is C40-50, will define the concrete and the rebar properties that will be taken into the design. We'll press modify to save this and we'll press close. Now we will select the design position. At that location the design will be performed. So I have already selected 128 and 129 element number, and moment and shear check will be performed at this location. Also we need to select the output position in order to get the Excel output at those particular location. Again I have selected element 128 and 129 for my output location. It is always recommended to select very few elements, those who are governing for generating the Excel report, as the Excel report is very comprehensive and it may take some time to generate. In serviceability load combination, based on the auto generated load combination, these combinations are auto classified into quasi permanent, frequent and characteristic. This is used for performing stress check and crack width check. Moreover, we need to define the loads, categorize the already defined loads into the short term and long term loads for performing stress check. Based on that, permissible stress is defined for a particular load case. Again, exposure class for the load case needs to be defined. Currently I have defined X0 exposure class for the elements. In shear connector tab, shear connector reinforcement is provided. So we'll select the 90-degree angle. We'll select the shear connector reinforcement. So I'll select 16 dia bar, 2 numbers and 5 bars in letter direction. It comes to be 2010. I'll press OK. I'll define the grade of the shear connector, that is 500 Newton per square. I'll press OK. I'll select all the members and I'll click apply. The shear connectors will automatically get applied to the composite sections only. After defining all these parameters, I will click on perform design option. So the design is completed now. Let's take a look at the results. So we have a flexure result table. At element 128 we can check the flexure results. Also we have a shear check table. Here all the checks you can see. This is the ratio for the shear check. The shear and torsion combined check table is separately given here. Also we can check the stress limits for various loads. Here this is the stress limit for loads at service stage. Moreover, when the structure goes in tension, the crack width check is also performed. Currently this structure is not in tension, that's why check is not performed, but I have another model where I have done this. So let me switch to that model. So this is the shear check table. Here as we can check, look at this table gets activated. This is the shear check results. As we can see, this is the crack width and this is the permissible crack width. So this is how it presents the results. Now let's take a look at the Excel report generated by this. So this is the Excel report generated. Once we click on it, it will take some time to generate the Excel report at the given output position. So this is the Excel report generated for the PSC composite girder. As we can see, the section properties, material properties are defined and is mentioned over here. This is the moment check done for this at this particular location, positive moment as well as for negative moment. Also check is performed for shear resistance over here. Again, check is performed for the torsion as well, torsion resistance and the combined shear and torsion based on the parameters defined in section properties. We have the stress check during construction stage and during service stage here. So if the tension in the girder exceeds the permissible limit, then crack width check is also performed at that location. Currently it's not the case, that's why crack width check is not mentioned over here. So we have covered from modeling to the design of PSC composite girder bridge. Let's go to our presentation now. I believe that this webinar would have given a fair idea about the capabilities of Midas Civil and various features that can be used to quickly design a PSC composite bridge. That's it from my side. Thank you. For technical queries, kindly contact our global technical support, that is globalsupport.midasuser.com.